Okay, for today's lesson we're going to look at electronegativity, polarity, and bond type, predicting bond type based off of electronegativity. It's a pretty simple lesson, so don't try and make it any more complicated than it needs to be. Let's start here by reviewing electronegativity. This is one of the trends that we talked about in Unit 3, which is the measure of how well an atom can attract electrons. Now remember, we said that electronegativity is the highest at fluorine because it's small and because it's missing that one valence electron to give it a full octet. Also recall that on our chart we don't have the noble gases here because the noble gases have an electronegativity value of 0 because they have full shells and of course do not need to pick up any additional electrons. I said when we looked at that lesson that we were going to come back to these values here, so now we're coming back to these electronegativity values. Mind you, you won't need to memorize them. There are some tricks that I will teach you to determine bond type without looking at electronegativity specifically. So let's talk about atoms and electrons. So we've talked about this before. Every atom wants to be like the noble gases and have a full octet of valence electrons. And that has to do with stability. Well, atoms are seeking stability, and they're going to do that by either gaining electrons and losing electrons to become ions, or in this case, we're going to share electrons. How they reach that octet depends on these electronegativity values. We'll spend the whole rest of the unit looking at covalent bonding, which is the sharing of electrons, but there's a very simple way to determine how an atom is going to fill its octet. So in ionic bonding occurs generally, this is sort of your rule of thumb here, between a metal and a nonmetal. Okay, so metals being on the left-hand side of the periodic table, nonmetals being on the right-hand side. So when there is a large electronegativity difference, causing one atom to lose electrons, the other one accepts them. That's because if you notice here, chlorine has a much larger attraction for electrons than sodium does. And so what it is going to do is it's actually going to pull that electron away from the sodium. And when it does that, chlorine now has a full octet, right? And sodium has an octet underneath. It's lost that outer shell. So it's got a full shell underneath. Sodium gets a positive charge, chlorine gets a negative charge. And we'll talk about the actual electronegativity difference values in a minute. But again, your sort of rule of thumb here is a metal and a nonmetal. The properties of your ionic compound, they have incredibly high melting and boiling points. They're crystalline structures, they're salts. All ionic compounds are salt, and not just table salt. Any type of ionic compound is classified as a salt. For instance, the magnesium salt, the Epsom salt that you put into your bathtub if you have sore muscles, is magnesium sulfate. It is an ionic compound and it is still considered a salt. They're generally water-soluble, meaning that they can dissolve in water. And they can conduct electricity when molten. That means when they are melted. Or when dissolved in water. They cannot conduct electricity as a solid. They have crystalline structures. If you ever look really, really close to a grain of salt, you'll see that it looks like a tiny little crystal. And what's happening is that their ions are lining up in this very orderly fashion to create a crystalline structure of alternating anions and cations. Because they're in this alternating form and any one atom is attracted, has the electrostatic attraction between all the surrounding atoms, that's what accounts for that really high melting point and really high boiling point, because there's a lot of attraction around that one particular atom. Covalent bonding is our next type of bonding. It's between two nonmetals, so a nonmetal and a nonmetal. This can be broken further down between nonpolar covalent and polar covalent. So if you have, I'm going to start here with polar covalent. So when you think of polar covalent, I want you to think of like the North Pole and South Pole. Okay, so what that's saying is that it's polar like a magnet is polar, right? I have one positive end and one negative end. And we'll look at this more later as we sort of progress through this unit. But this is a very uneven sharing of electrons. Notice here that this chlorine is really working to pull that pair of electrons away from that hydrogen. Whereas with a nonpolar covalent bond, these electrons get shared relatively equally over two atoms. Properties of covalent compounds, they're the opposite of ionic compounds. They tend to have low melting and boiling points. They're generally flammable. They're very poor conductors of electricity in every phase, right? Dissolved in water, as a solid, as a liquid. They're just bad at conducting electricity. And they exist as discrete molecules, so they don't make that same crystalline structure that you see with your ionic compounds. So nonpolar covalent, so we'll come back to this. So I have an I have an even sharing of my electron pairs. And you can see here that my electron cloud pretty evenly is distributed over those two chlorines. This occurs when the electronegativity values of my two atoms are roughly the same. They don't have to be exactly the same, but they should be pretty close together. And that just means that one atom, even though it's bonded, doesn't particularly have an attraction for an electron more than the one that it's bonded to. In polar covalent, you see an uneven sharing of electron pairs. And so you get electrons pulled to one side over the other. And we know that electrons are negative. And so if I pull all of my negative electrons over to this side, I get what's called a delta negative, which is a slight negative. It's not a full charge, but it's a slight negative. Slight negative charge. And where I have a slight negative charge, on the opposite side, I should have a slight positive charge. And again, that's because you're pulling the electrons to one side over the other. Okay. Here's another great example. You can see the delta negative here. Bromine has a higher electronegativity value, and so it's pulling the electron cloud away from that hydrogen. We can signify this by writing a delta positive and a delta negative to represent which side is positive or negative. Or we can draw a polarity arrow. So over the side that would be positive, that has the lower electronegativity value, you draw a little plus sign, and then you draw an arrow which represents the direction that your electrons are flowing. So because bromine has the higher electronegativity value, the electrons are headed towards the bromine and away from hydrogen. So determining bond type through electronegativity difference is very, very, very simple. I don't want you to overthink this at all. All you have to do is find the electronegativity value of the two elements and then just subtract largest minus smallest. So find the difference to determine what the bond type is. So if the numerical difference is between 0 and 0.4, you're dealing with a nonpolar covalent bond. If it's 0.5 to 1.7, then it's polar covalent. If it's ionic, it's 1.8 and up. These are rules of thumb, so they're not going to be exact everywhere. I'm also not going to make you memorize this, but you should know generally that if I have two elements that are very close together, they'll probably be nonpolar as opposed to two elements that are far apart, and those being ionic. And again, go back to that idea of a metal and a nonmetal is ionic, and 2 nonmetals are covalent. So we'll walk through an example, but super, super easy to do. Before we hit this example, I want you to see this. So this is what I was saying, that this is kind of a rule of thumb. So this is what your electron cloud would look like if it's nonpolar covalent. And then this is what it would look like if it's polar covalent. So we sort of define these barriers at 1.8 that it becomes ionic. But in actuality, it's kind of a range. Like we don't just immediately snap apart into that electron transfer. It's just that the electron gets pulled closer and closer and closer and closer to the other element until at some point it's considered to be a part of that other element's electron cloud. But again, like, it happens gradually. It doesn't just happen at 0.4 and at 1.8. Alright, so let's do an example. So what type of bond would hydrogen and nitrogen make? So I come here, I find hydrogen, that's a 2.1. Nitrogen is a 3.0. Super easy. I just do 3.0 minus 2.1, and I get 0.9. So if my difference is 0.9, it's polar covalent. Okay, and I'm going to go ahead and draw my polarity arrow. So I'm going to do nitrogen with a 3.0 is bonded to hydrogen with a 2.1. Hydrogen being smaller is going to have that positive sign, and my electrons are being moved over towards nitrogen. Let's do another one. What type of bond would phosphorus and arsenic make? So I've got phosphorus here. I've got arsenic here. Okay, 2.1 and a 2.0, so the difference between 2.1 and 2.0 is 0.1. So it's considered nonpolar covalent. Even though there is a slight difference in electronegativities between phosphorus and arsenic, I'm not going to draw the polarity arrow because it's considered nonpolar covalent. Another one here, I've got sodium and I've got fluorine. Now right off the bat, you should know I've got a metal and a nonmetal, so I know it's ionic. But just to prove it, we'll say 4.0 minus 0.9 equals 3.1, very ionic. Right? I'm not going to draw polarity arrows because it's not a polar covalent bond. I'm just going to draw it as Na plus and F minus. Right? I want to signify that the full charge has moved over to the fluorine. So there is a third type of bonding, and it's metallic bonding, and it only occurs between metals and metals, hence why it's called metallic bonding. So metals versus metals is metallic bonding. You're not using your electronegativity values for this, but what you have is you've got the cations of all of these metals sort of surrounded by this sea of electrons. And I want you to use that terminology, sea of electrons. Right, so these electrons are considered delocalized. They don't belong to any one atom. And so because they're delocalized, they move around and they hold all of these metals together. Because of that, electricity and heat move really well through metallic bondings. It's because of those delocalized electrons. And then what you can do with metals is you can have alloys, right? So when I have a mixture of metals, it's called an alloy. So I have a substitutional alloy where I replace, in this case I'm placing copper and a bunch of nickel, or I can have an interstitial alloy where carbon is between the iron atoms here. So those are our two types of metal mixtures. So that's it for the lesson. The rest is just homework. And we can talk about it when I return on Thursday. Okay?